I think we're going over now. Welcome to Live with Lil, episode 207, where we're going to be watching Writing on the Wall. I'm so excited. I'm more nervous this week than I've been for any week, just because we've got the most amazing brains on today. I'm going to do
really well caffeinated for today's.
So much coffee. Trying to get my neurons firing, you know. So just a little introduction. We have Virginia Dessar. Virginia is a professor in the Department of Cognitive Science at UC San Diego. And I didn't know how to say this word. An associate director of the what is that? The data. One more time.
Halle-Julu Data Science Institute.
Oh my gosh, see, it just sounds so right. I'll learn that for next
time. That sounded effortless.
And it says here, your research goal is to better understand the neural basis of human perception and learning, both from a neural and computational point of view, and how you investigate the computational properties of machine learning algorithms and what psychological recordings and the constraints and limitations of human performance tell us about our brains learning. So that I feel like I didn't say that maybe as good as it sounded in my head, but anyway, so happy to have you. And along with Ginny, we have Andrea Chiba. Okay, I'm going to embarrass you with your bio. Andrea is a professor in the Department of Cognitive Science and in the Program of Neuroscience at the University of California, San Diego. Andrea has her own laboratory team that's focused on gaining an understanding of the neural systems and principles underlying aspects of learning, memory, affect, and attention, with an emphasis on neuromodulation. I mean, could you be any more starstruck? Thank you so much for being here.
Thank you so much for having us.
Yeah, thanks for having us. We're kind of starstruck too, actually.
Oh my gosh, well, I hope that by the end we'll all be,
Yeah, buds.
Buds.
Best buds.
Right, let's go ahead and press play. I'll do a little countdown. And then that can get ticking over in the background, the episode. So for everybody watching at home, we're on the Marvel flip. So if you're ready, I'll do a little countdown. Ready? So 3, 2, 1, play. Okay, off we go. Good. So many questions, and I know we're going to get a bazillion in the chat as well. Zach is monitoring the chat, and he's going to be really focusing on it this week.
I promise.
So do put your questions in there. Would you mind each of you just kind of saying a bit about what you do and what your focus is? I know I read the bios, but I feel like you would do it maybe better than me, maybe in layman's terms. So Ginny, can you kind of introduce sort of what you do in your area of interest?
So my area of interest, it's very interdisciplinary. I work both on machine learning algorithms, which is getting the computers to learn like humans do. You've probably all seen a lot of machine learning in action nowadays with self-driving cars, and even when you talk on the phone and you say things into the phone and it understands, that's all using machine learning. And even automated face recognition. There's a lot of machine learning out there. So I work on algorithms for that. And I also, at the same time, try to understand how the brain works. So a lot of the algorithms we use for the machine learning are very similar to the way we think the brain works. And in fact, they're motivated by the way we think the brain works. So at the same time, I'm very interested in studying how the brain works, more from a computational point of view. So Andrea knows much more about the brain than I do, but we learn enough to be able to help motivate the machine learning algorithms, and often the machine learning algorithms can also give us new insight into the brain. We also do a little bit of work on brain-computer interfaces, where we actually have electrodes externally on the scalp. So just you can put some conductive gel, you can put some electrodes and actually read the voltages at the scalp, which are related to the electrical currents that are going on in your brain as you're thinking. And so you can't you can't read everything that people are thinking, but there's certain brain signals that can be detected to some degree outside the brain. And so we work on better systems to read that brain activity. And that's called brain computer interfaces. They were originally developed for people who were totally locked in, so are unable to speak, move their eyes, or especially move their arms, walk, etc. So they have no other means of communication. So this was originally developed as a way of communication for people like that. Now though, there's also applications in gaming. It's kind of fun to do something with your brain besides using your hands for other things. You don't get anywhere near the bandwidth of communication that you do by speaking and by using your hands, but it can be used as another pathway for information. So
wow,
those are
oh my
largely
gosh.
the work in.
I mean, I have so many questions just from that, but Andrea, I want to give you a chance to say a little bit about what you do as well, and then we've kind of got both sides of the picture to sort of move forward, if you wouldn't mind.
Yeah, so I study how neurons in the brain and how the interactions between neurons in different brain regions support behavior. And I'm interested in how we learn, primarily how we remember, and how things like our emotions and attention change what we learn and how we remember. And I'm interested in how the brain is organized to support all that and how it arises from the brain. And we also develop some kind of computational techniques to examine those dynamics.
Wow. I mean, just fascinating. So I'd love to just pose before, because in this episode, Coulson is volunteering to go into the memory machine as his memory has been wiped, and he's trying to remember details of what happened in Tahiti, which was brought agents back from the dead and wiped their memories of the process of it. That happens later in the episode. So when that pops up, I'd love to talk more about the memory machine and kind of if that would be possible and that process. But just until that comes on, Fitz in the show plays an engineer, which I feel like is probably maybe your Fitz, Ginny, and maybe Andrea, your Simmons. The equivalence kind of. So he has brain damage from the season 1 finale when we almost drowned. Just thinking with both of you talking, it kind of made me think of Fitz and the damage that he's had done to his brain. And, Mac in this episode says about gaming helps to kind of rehabilitate the neurons in the brain sometimes. I don't know if either of you can speak to somebody like Fitz that would you ever work with people like that, or have you studied people that kind of have gone through some brain damage and how you rehabilitate, or would that be more your area, Andrea?
Yeah, I started out studying people who've had brain damage and memory loss through various routes. Some of the people that I studied early on actually had something similar happen because they had anoxia. So they had a lack of oxygen, which is basically what happens when you almost drown. And in fact, the areas that are involved in learning and memory are most vulnerable to the lack of oxygen and die first. And so often memory loss is one of the problems you have. And then Ginny's worked more on the rehabilitation end.
We haven't done any specific rehabilitation, but the brain-computer interface technology is used, among other things, for rehabilitation, often rehabilitation after strokes, when people can't move their arm. So when you have physical therapists, they'll move the arm while the person is trying to use their brain. I mean, the idea is you want the brain connection to the arm to improve, right? But if they can't actually move their arm, it's hard to get that pathway strengthened. So the physical therapist will move it. But there's also the brain-computer interfaces can actually detect that you're doing the right brain activity, even though the link might be broken. And so that can be used to help either a robotic manipulate or move the arm, or a physical therapist to move the arm at the right time when they've got the right brain activity. So brain-computer interfaces can be used for physical therapy like that. I had one undergraduate student in my lab who actually had a very severe concussion and brain damage from, I believe, a motorcycle accident. And he was very motivated to study brain-computer interfaces for the reason of improving brain. Like he'd recover, but it had taken a long time, and he was interested in helping to improve recovery.
Oh, interesting. So you would have a model of what an unaffected brain would be, and then you would have the affected brain. And based off of where the neurological activity would actually be, you would say, so this is where the robotic arm should receive a signal to do this movement. And so then you would try and replicate what the unaffected neural activity would be sending as a signal. Is that kind of, am I following you correctly?
I think so, yeah. Basically, there's the desire to make the arm move, and then somewhere in the connection it's broken. But the idea is if you can pick up some aspects of it, then you can help to basically, by moving both systems together, you can help increase the strength of that pathway to allow in future that the actual desire to move can lead you to move.
Right. So say with Fitz, one of his hands shakes, which for me as an actor, that was such a trigger to me, because I mean, I was obsessed with Fitz just as Elizabeth. So whenever I was in a scene with Ian during this kind of Fitz doing having brain damage and still recovering, he has a little shake in his hand, and anytime I saw the shake, it would just make me want to cry, because I don't know, I was just so sad that Fitz was injured. So say somebody like Fitz that has brain damage that then affects, say, his arm, you could, as a way of rehabilitation, you could put whatever gel and nodes on his brain and kind of say, lift your arm, and you would then be able to see on his brain scan a certain area of his brain light up, and when it does, somebody could lift his arm for him at the same time as he was thinking, to help to those pathways to kind of rebuild.
Yes, and then Andrea can talk more about the Hebbian plasticity, but the idea is if two neurons fire together, you increase the strength of their connection. So the idea, and then also if the motor activity is happening at the same time. So the idea, yes, is by forcing it to happen together, you can help to increase the strength of that connection so that next time it can happen more causally. Andrea, do you want to add something to that?
Yeah. I mean, in animals, actually, you can actually measure change across time, and they'll remap. So they'll use whatever brain they have left to try to make those mappings again. And sometimes you'll get things like shaking, et cetera, because the balance of excitation and inhibition is off. So that's another thing that you can kind of train, is that balance. So
Wow.
that's the basis behind sort of like neuroplasticity from a 35,000 foot view, right? Is that you have the areas of the brain that may not have been associated with that activity can actually build a pathway to produce the said activity. Is that?
Yeah. And right? you need to have the right neurochemicals present too. So that's very important also. So we talk a lot about the electrical, but the chemicals super important too.
Oh, wow. And is that something? Oh, go on.
Andrea's the expert in the neurochemical.
Somewhat.
So I hadn't even thought about that. So the neurochemical, I mean, I feel like it's chemicals in the brain, right? But is there a way to, if you've, say, had brain damage, or I don't know, hormonally, can that alter the neurochemicals in your brain? How do they get disrupted?
Yeah, because people kind of forget about the fact that like the top of the brain, the cortex, doesn't make, I mean, it makes a lot of neurochemicals, but it doesn't make all of them. Some of them come from pathways into it. And so if that pathway going up is broken, then the chemicals can't get there. So like reconnecting also allows the right chemicals to be there.
Oh, I see. And is there a point that your body ever just, you know, if it can't, say the neurochemicals can't get to the place it needs to go because of, you know, a physical obstruction there, is there like, does the body then stop making those chemicals, or like, do you ever have to do them synthetically, or will
Yeah,
they
people
always be?
add synthetically, so they medicate. The thing that kind of relates to this episode, though, is if you add synthetically, it kind of drowns it and the timing is off. And the brain has these various ways that it likes to time things. And brain waves are one way that it times things. So things tend to go in waves. And so if you get things that are just, you know, if you just sort of drown the system with the whole chemical rather than getting it there at the right time, like a pathway would, it doesn't have the same impact entirely, but it can partially restore.
You can also restore by stimulating the brain itself. So in Parkinson's disease, they have deep brain stimulation, and they stimulate the area that generates the dopamine. And Andrea can, but and they can do that somewhat physically. You know, they can make that better and better, and that can, you know, help in Parkinson's where there's this deficit in dopamine.
Yeah, and that's a great
Wow,
example of restoring balance, actually, excitatory inhibitory balance.
So they have drugs
Yeah.
they can give you externally, you know, the precursors of the neurotransmitters, but they can also do the stimulating where they're stimulating in your brain to generate it yourself.
Wow. So we had a question by email from Kirsty, and I'm just going to hop in with this now, if you don't mind, just because with you mentioning Parkinson's, she asked, she said, I was reading a couple of Ginny's papers that had been published in recent years, and I was just wondering if this line of research could lead to an improvement in treatment or even a cure for memory loss conditions such as Alzheimer's disease. Would understanding how we make and recall memory aid drug development, or are they separate entities? That's so interesting that you mentioned Parkinson's, that it seems like that's an area that this kind of research is helping to treat, if not hopefully one day cure. Is that kind of right? That the kind of the work that you guys do is also used to help Parkinson's?
I think Ginny's, yeah.
Oh yeah, sorry, my internet cut out while you were asking that part of it, so I didn't hear all of it.
Oh no.
It's not directed to the cure of the disease, but the amelioration or the improving the, you know, the state and the living conditions. It's brain computer interfaces definitely are doing, you know, are working towards that for Parkinson's disease.
Wow, that's just so incredible.
Can you, one of the things that we do a lot of times online with those, just how people got involved into their
I might
disciplines.
need to interrupt you in a minute because we're about to go into the memory thing.
But if that's something, because you've obviously gotten quite specialized into your field. So where did you start? And then I think, like, specifically for me, it's like machine learning is something that's just like thrown around these days, that as almost something that's quite of this time. But when you actually start reading about it, it's been around for like 50, 60 years or something, right? So it's like, how did you both go from, you know, you went to college, what did you think you're going to study? And then how did you go down this like rabbit hole to get into such specialized fields and, you know, and rise to prominence?
Andrew, do you want to go first? Or do you want me to?
Oh, I'll go. So mine was an odd path. I couldn't decide what to major in college. I liked biology and physiology a lot. I liked psychology a lot. And I liked math a lot. So I took all at once. My roommates were engineers, so I sort of took math socially with them. And then I studied psychology. And then I thought I would take some time off before graduate school because I didn't know what I wanted to do. And I actually was doing research on a project that was funded by Steve Wozniak, one of the co-inventors of Apple computers, because he'd been in a plane crash and developed amnesia for a short period of time. So he was interested in memory. And so he funded our lab way back when, with a little check signed by Woz for $250,000, little garden check, to study patients in recovery from head injury. So at the Bay Area Head Injury Recovery Center, I worked as a research assistant studying people who had basic head injuries. Actually, while I was a math teacher too, I was a high school math teacher at Menla School in Atherton. And anyway, I met a woman who just had a baby and she had total retrograde amnesia, meaning she had no memory of her past. And we showed her a picture and she's like, that's me, but whose baby is that? And we studied her as a case study. I got so interested in the brain and learning and memory that that's how I went to graduate school in neuroscience. So,
and she
anyway.
just lost her memory through, was there an incident?
She had a virus that got into the brain, and she had what was called viral encephalitis, and it expressed, and it went straight for the temporal lobe, an area of the brain that's involved in learning and memory, and did damage. And it took them a while to figure out that she had this virus. And so it did some damage. And so anyway, the rest is
wow, that's amazing. I mean, it just shows you too that you studied, it sounds like you did what you were passionate about, and then through very human interactions that affected you on a personal level, kind of had that motivation to then to use that as your driving path educationally. And I think that's so cool to hear, because I know for my career, I didn't necessarily always know what I wanted to do, what that career looked like, but I did know what I was passionate about, and so followed that, and then that went on to open different doorways. And you know, I think that's something that I just love hearing, that you didn't start out knowing what you wanted to do. You kind of allowed yourself to be led by your passions. And I mean, you just saying I did maths socially because my friends were interested in maths. I mean, that's so cool, because I never even thought about doing maths socially. It's like,
yeah,
that's just
weird, right?
You know, it's so cool. Ginny, what was your path like?
Somewhat also very scattered. So when growing up, I knew I liked math and science, but I didn't know what I wanted to do with it. And I liked math a lot. And my dad recommended that I do engineering, and I didn't even know what engineering was. But I was told if you start in engineering, you can switch into any of the sciences without losing a year. And if you go the other way, you lose. So I thought, okay, fine, I'll do engineering.
Oh, I love it.
And so I went to Queen's University in Canada, where first year engineering program is consistent for the whole program. So, you know, you don't have to decide at that point, you just do engineering. And then I picked math and engineering again, because I still really liked math. And then I picked the electrical engineering option of the math and engineering track. But along the way, I worked for different labs in the university. And then I got really interested. I was interested in how the brain worked. I mean, I think I was always interested in that, but I didn't know what the best way to approach that was. And so I worked on an artificial intelligence project, and I really liked that. So then I applied to grad schools in computer science, but I didn't have a computer science undergrad degree, of course. So that was, so not all the places took me, but I got into a few, and I visited, and it was nice and sunny when I visited one, and not so sunny. So I went to grad school in computer science with the idea of doing artificial intelligence, specifically natural language research. I was interested in language learning, and also how you learn different languages. But when I started in natural language learning at the time, it was all a bunch of entering rules. So people would be programming in all these rules, and then that was going, that would basically form the language. So a sentence is a noun phrase and a verb phrase, and a noun phrase has a determiner, and I was like, wait, no, this is never going to work. So that's when I got interested in what's called machine learning, where the machine learns just from a large amount of data. And the person doing machine learning at Rochester, Dana Ballard, was doing neural networks for machine learning. And so that then got me interested in neuroscience and learning about neurons. So I took a lot of neuroscience classes, mostly not for credit. But I learned a lot about neuroscience, got very interested in neuroscience. And then for a postdoc, I decided to do a postdoc in, there was a Sloan Schwartz program where they brought in people from computer science, math, and physics to learn about neuroscience. So it was a great opportunity to learn more about the brain, learn more about neuroscience with other people who didn't have that biological background, but had computational background. So then I did that, and then I got hired by the cognitive science department, which is great because they have computation, behavior, and neuroscience all mixed in together. So it's a perfect department for me, and I guess also for Andrea. So that's how I got there. And then brain-computer interfaces came later. I had a graduate student who was interested in brain-computer interfaces. He was an engineer. He was excellent. So I thought, okay, fine, we can head that way. I mean, I trusted that he would, be able to lead the way because I didn't have the background at the time. And I was interested in actually doing something useful with the machine learning. And so that's how we got into brain-computer interfaces. Like, oh, well, let's do something useful. And it's related to the brain, it's related to machine learning. It seemed like a great application of machine learning to both learn more about the brain, but also help people.
Yeah. Gosh, I feel like we need to make epics about both of your journeys. It's so, and obviously, they're not over. You're both, it feels like led by passion and also opportunities when they arise to, when you hadn't necessarily thought of combining two different disciplines and how that can, as you say, help people. And I mean, I'm completely blown away. We're seeing now Coulson in the memory machine. So I don't necessarily know who maybe could answer the question, but what I would love to talk about is a memory machine, is that something that could at one point be possible, or do they exist? Can you hook the brain up and access memories that people can then see as a dream, or is this just totally science fiction?
Andrew, why don't you start?
Well, right now it's science fiction, but one thing that I noticed was that, they talked about the machine driving theta, right? And so what is that? Well, the brain is actually a giant oscillator. So it oscillates at all these different frequencies. So the brain has these waves, these rhythms that go at different paces. So theta is like 4 to 7 cycles per second, or 4 to 7 hertz. And so that cycle is very much involved in memory. And so it is one of the brain waves that is important for learning and remembering. Matter of fact, at the peak of the wave, you're more likely to remember, and at the trough, you're more likely to encode. So it's, there are all these studies. And then there are other rhythms too they could have used. Some of the faster rhythms are actually good for getting the memories out. So
wow, so then you would put those rhythms, say on a, I don't know, like stick a note to the brain and put that frequency of wave through the brain to.
Yeah, I think that's what they're trying to do in this machine. I mean,
Right,
it's interesting because in animals, actually, they've managed to virally infect just a few neurons and then activate them with light, and they can actually bring back a single fear memory for a rat by activating just this one array of neurons that was there when the memory was made. And so they go into the brain and just activate just these few neurons with light. So, I mean, if you could do that in humans, technically, and you knew which memories, technically you could kind of activate.
Like they would just hide cheese behind some hidden door that they never knew was there before, and then they'd activate it and it would know that, like, I mean, I'm simplifying it, but like, how would they know that they're activating that specific?
Yeah, in this case, they scared the animal in a particular context, and they had the neurons, they labeled those neurons that fired at that time. And then they went ahead and they put a virus in there that was actually could be activated by light and turn the neurons on. And so they turned the neurons on and they reactivated the context, the time and place for the animal.
How interesting.
And so it is kind of crazy. That's the most similar thing I can think of in terms of like actually being something you could do. I mean, in this case, they were trying to use the rhythms, and you can, get the brain into a different state by driving different rhythms. I mean, that's how, like, if we have seizures, our brain goes into a different state because we have different activity going through this area, the temporal lobe and the hippocampus, which is involved in memories and memory formation. And so, you can change the kind of time space parameters of the brain by changing the waves in that area.
And you can stimulate the brain externally in humans with electrical or magnetic stimulation. So there's something called transcranial magnetic stimulation and transcranial electrical stimulation. It's pretty crude. It's not anything like what Andrea talked about activating specific neurons, but you can target different areas. So you can have a coil that generates a magnetic field. You can target where that field is going to go, and you could presumably activate different you could set up different oscillations and frequencies. And then, of course, in patients, they can do invasive stimulation where you actually have electrode going into the brain. You don't do that in regular healthy people, but you can do that. So when Andrea mentioned seizures, you can actually detect. So again, using BCI type technology, you can detect when seizures are about to happen before they happen. And then if you can stimulate, you can actually prevent some of the seizures from happening. So there is some simulation done on people. Again, that's a little different than the memory stimulation for memory, but there's some of the baseline technologies are there. But yeah, it's still science fiction, what they actually show in your science fiction show.
I just have a question about this is so fascinating, but the first question, like, so when they can detect that a seizure is coming, is that because they can see a part of the brain lighting up, or there's a frequency level that they can see the amplitude increasing, or am I just like completely?
So when you say lighting up, that sounds like sort of when you put people in like the Fmri in the scanner, the Fmri scanner.
I'm just looking at the picture behind you, and I'm like thinking that like one little.
Okay, the picture behind us is actually made by Tim Mullen. We should
give Tim credit.
He was a graduate student in our program in cognitive science, and it's a simulation of brain activity recorded with EEG. So normally with EEG, we don't talk about lighting up, although he did make this beautiful light up. But so yes, there is also Fmri where people, where you see the little blobs of color in the brain. The problem with Fmri as a measure of predicting seizures, the Fmri is done in like a big, huge, expensive magnet. And so you can't drive around in your big, huge magnet and detect when your seizures are. But EEG is actually quite portable. And so from the EEG, you're measuring the voltage signals over time. And from that, yes, you look at changes in specific frequency, and the ratios of different frequency bands is largely what you're looking at. There's not so much spatial resolution in the EEG because there's a lot of blurring by the time you measure the voltages at the scalp. Tim worked with the Schwartz Center at UCSD that does very sophisticated. He used many electrodes, and they do very sophisticated source modeling to actually try to get at the source locations of the brain activity they're measuring, and that's what's in the video. But you need a lot of electrodes to do that. But even with just simple frequency analyses, you can detect seizures before they happen. Yeah.
Wow.
And if someone's going to have a temporal lobe seizure too, one thing that happens is you get like a spike wave discharge deep down. So you get these weird spiky things. And then what will happen is it'll send the cortex. It's like talking to the cortex and sends it into these slow waves that are really synchronous. And so you can read out the synchronous slow waves from the temporal lobe.
Can I there's been a question along this that Emily's asked. She says, is it possible for what Lincoln did to Werner von Strucker to happen in real life? So he zapped Werner's brain with his electricity powers and helped Werner break out of a memory loop. So it was a character that was kind of couldn't stop reliving this one memory. And then Lincoln had powers of shooting electricity out of his hands, and he kind of shot the electricity at Werner's brain and broke the kind of memory loop that he was in. That could that sort of be possible?
Somewhat.
I mean, there is something that was used way back, right? Electrical shock therapy.
Yeah, electric convulsive shock therapy,
which they would use to get people out of severe depression, right? Is that what they, which in some ways is being stuck in a depressive state. And so, yeah, I mean, if you shock the brain, you're going to change the electrical activity. Probably the least
totally disrupts memories, though. It does.
So
yeah,
that the shocking and pulling you out of whatever brain processing you're in is totally true. I mean, probably the weirdest part or the most fiction part of the other thing is if he's like stuck in just one memory loop over and over. That would be a little too specific. But shock, electrical shock to pull you out of, to totally change your brain processing. Yeah, that's definitely true.
Okay. I hope that answers your question, Emily. The other question that we've had a bit is it possible to, if you can map the brain and put enough electrodes on, is it possible to download a human into a microchip?
Into a hard drive, and then...
So people say, not yet.
But you're asking theoretically if it was, I mean, right now it's not possible to record every neuron. But you're saying theoretically, if you could you store, I mean, you would need to store every connection between every neuron if you really wanted to
duplicate it or replicate
it.
or...
If you wanted to duplicate it at this point. I mean, it's possible that there's some compressed way you could save it, but not yet.
So this is,
I mean, you could get the net output from the cortex, but that's missing so much that, there's not enough to know from that.
Okay.
I think my other question, I'm circling back because I had a question about the when it's anticipating seizures, and as it pertains, I guess, to machine learning, is what you would basically do is collect all of this data, and then algorithmically you would set up I suppose like the end goal would basically be to develop something based off of that machine learning that could kind of intersect when you see sort of the seizure coming, and whether that's something that you wear or however you would do that the machine learning would be able to do to anticipate that that's happening, and then you'd be able to stop it. And that's through a set of algorithms, or like how complex is, I guess it's not one single source code algorithm, right? It's like a sequence of thousands of algorithms, or how are those interacting?
The way the machine learning works is it's basically doing pattern recognition. So it learns from what's called big data, lots and lots of data of previous examples. So you get basically whatever wherever you want to record from. If this is going to be something that people use in their everyday life, you want very few electrodes. So maybe it's a couple of electrodes across your forehead that's under a baseball hat, or some wearable form factor that people, and then you need to get data from people that will go into seizures. So you get many, many examples of EEG data, and you label, you get, a clinician will label their seizure happened here to here, etc. So then you can go back and you can chunk segments. Okay, here is 2 minutes before a seizure. And here's 2 minutes not before a seizure. And you get a whole bunch of this. And then the neural network algorithm, which actually learns somewhat similar to the brain, is called neural net. But basically it adjusts the weights on these connections to learn the patterns, to learn, okay, when this kind of signal leads, tends to lead
X
to
and Y,
etc. But it's basically doing pattern recognition like that. And if you do this just on one person, if you developed a system for each person, you trained it with their data, you would do better than if you have a more generic system that would work, like you stick it on your head and it would work, and you stick it on. So it's a harder problem to make it work across people, but people are actually doing, I think there's a company actually working on this specifically for seizures right now. I mean, it's a very useful thing, right? Because there's people who will have seizures, and if you get a 2-minute warning, you can, if you're driving on the freeway, you can pull off, right? So you pull off so that when you have your seizure, I mean, even if you can predict and don't actually manage to prevent it, if the person knows to pull off from the freeway, or, stop operating the machinery they're doing, or whatever, put the baby down, whatever it is you're doing, if you get a 2-minute warning, you can prevent a lot of damage. And then, of course, if you can actually stimulate, and this is not the kind of stimulation that like totally zaps your brain, but this is like a small focal stimulation. If you can stimulate and actually prevent the seizure, then that's even better. And if the simulation is actually kind of mild, then you don't need to get it perfectly. You don't need to be 100% right. So a little stimulation, when you didn't need it, as long as it's not.
It's like when your partner's snoring and you don't want to wake them up. You just want to like kind of like, hey,
Pinch them.
yeah, just a little bit, just a little.
Sure. I had some quick questions about in the episode, the main guest star of the episode talks about how pain can helps him remember. And then I know through acting and stuff is that people, sensory memory is a technique that we learned during training, that some of my friends were very I guess triggered emotionally by smells, and that would take them straight back to a memory in their childhood that they could then tap into in a particular scene. I don't know, can you talk about kind of how the senses, or even just something like pain, can help to unlock memories? And is that a technique if, to do memory exercises, or is that a real thing?
Yeah. So there are many different routes for forming memories. So we think of a memory as one thing, but it's very distributed. So every different system has some trace of the memory. And so, in fact, there's an area called the amygdala, which projects to every different neurochemical system. And it's just like attached to your hippocampus, this other structure that's very involved in learning and memory. And so if something's very emotionally arousing, it kind of hard stamps that memory. And so you can have that memory endure even independent of having the other memories missing. So if something's very emotionally arousing, you can have a separate trace of the memory. And so you could take someone's hippocampus out, but there might be a preference for a place still, or some other form of memory.
Wow.
So I think what Andrea's saying is part of what the pain does is it activates a lot of these neurotransmitters. It's the neurochemicals that she was talking about earlier play a big part in learning and memory.
Yeah.
Wow.
The thing you said about smell is also interesting in a different way. So the olfaction is the only system that doesn't go through the thalamus. Most of the sensory systems go through the thalamus to get to cortex, which is again the outside part. And so the smell has this more direct pathway, and so people think that that's why smell is so evocative of different memories.
Do you think that's just sort of like through survival of the fittest? Like why would olfaction be prioritized over all of our other, or is it not prioritized? I guess I'm just making that assumption, but it's like, if it's bypassing that, doesn't it sort of indicate that it's?
Yeah, I mean, some of the other senses do too. Now we know, truth is, but through different routes. But olfaction has like these big old projections. But I mean, you can keep yourself from eating toxic things that way. It was used for kin recognition. There are all sorts of olfactory things we don't understand that well. Like there are experiments done where you'll have two robots that were identical. This was done by Sobel, who studies olfaction. And one robot has fear odor, and the other robot just has some general odor. And people go in and the robots give them the same information, but they trust the one that doesn't have the fear odor more. Wow. And people don't detect any of the odors though.
Yeah.
It's super
interesting.
So fast, because I was thinking it's like you smell people, you smell fear, and I was just wondering like, how is that, is it hard stamped, as you said?
The olfaction system phylogenetically older Andreas that have been around longer, or is that?
I mean, it's very different creatures, so I'm hesitant to say that. It just depends which phylogenetic path, and I'm not an expert enough to comment on that, but like they use dogs for all these things we're talking about too. Like, a dog can sense seizures too. They have dogs that are specially trained to sense seizures. Dogs have like huge ability to smell things that we don't figure out all sorts
of COVID now too, correct? Like they're having dogs able to sense smell coronavirus, et cetera, et cetera.
I heard that. I don't know much about it, but I heard it.
Yeah, I heard it too, but I don't know. Also, I know I've also seen stuff about dogs being able to smell some kinds of cancer too, but again, I don't know.
Yeah, they can smell skin cancer, I think.
Wow. Oh my God. I mean, the episode is finished, but I feel like we could have gone on forever. Thank you so much for coming on. The Zoom chat filled up very quickly. I'm going to invite a couple people in to ask questions. I will be answering questions as best I can on the outro of the podcast too, if anybody has any other the questions that we've kind of missed in the chat because we've been so focused on the conversation. I did look at a few, and I think there's going to be some really interesting people in the Zoom to ask a question. It has been so fascinating for me to dive into Coulson's brain and kind of how he's experiencing this episode, and also with Fitz. I'm just so grateful to both of you coming on. It was such a fun way to watch this episode, and I hope that the people that are watching this conversation can help to inform other episodes of S.H.I.E.L.D. that they watch and kind of have a different perspective on what Coulson and Fitz are going through.
And I've realized that a lot of times I will just whisper in Elizabeth's ear while she's sleeping, pizza for dinner. But I'm now thinking I just need to put some smell there. And that will actually, that'll work a lot better.
Yeah.
I think so.
Better than the other smells you put out there. Okay. I'm going to invite Tabaluga Dragon. I saw that you had a really interesting question in the chat. So hopefully that person is coming in. Hi.
Hello.
How are you?
Oh, you're talking to me. Oh my goodness. Hello. It's just, there is a delay between the actual stream and Zoom. First of all, I wanted to thank you for inviting such amazing people for this, for actual researchers in this field. It's incredible to actually, thank you so much for coming, all of you. It's really, sorry, I'm so nervous. First of all, greetings from Russia.
Amazing.
It's literally almost 2 a.m. here, and it's
wow, that's dedication.
Thank you. First of all, I wanted to say for a long time now, that sorry to all the fans of Marvel movies, but Agents of S.H.I.E.L.D. just destroys them in terms of storytelling, soundtrack, character development. I guess, on most of departments. So my question is, I prepared it a long time ago. Question is for you, Elizabeth, and I wanted to ask about the episode for 4,722 hours. I really hope it wasn't asked before because I really want to know. The question is, how exactly was that episode of you being on another planet filmed? And what challenges did you face as an actress and the whole filming process? What difficulties did you experience in there?
Well, thank you for your kind words. I agree that we've just had the most amazing guests on this week. That episode we filmed out in the desert in California. We filmed it all in the bright, bright sunlight and then changed it in post so that it looked blue. And it was really fun. I mean, I'm sure we could at some point discuss the science of whether you can be sucked into a monolith and transported to another planet. But yeah, it was very fun. It was a little bit intimidating, but yeah, it was certainly hard work in the blazing hot Californian sun, but it was really fun. I'm glad you enjoyed it. I feel like I saw in the chat you asked something about intuition.
Yes, I wanted to ask, is it actually real? And if it is, can it actually be enhanced artificially?
Is intuition something that can be sort of traced?
Yeah, question for Virginia and Andrea. Yeah.
Yeah, I would say yes. I mean, there are different kinds of memory too. So some things are memories, even though they seem like intuition. Like if you took the episode, where they keep drawing things, even though they remember nothing, that sort of sense, intuitive sense, there was something they had to get at. There's something called procedural memory that they obviously maintained, where you can just keep doing these things. So they had some other kind of implicit, as you would say, sort of below awareness trace of something that they kept trying to like bring out. And then a lot of times we have something that's sort of a gut feeling, right? And so there are different brain structures that can be operating sort of along line, online, kind of iterating beneath our awareness. And that sort of gut feeling is something that we can learn to attend to. So you can learn to tune into your gut feeling.
Incredible.
There are ways to learn.
So the more you kind of tune into, the more you do what your gut is telling you, the stronger those pathways will become.
Yeah, I think so. I think we can develop various ways to have to attend to different things. Like if you want to scan the environment and be hyper aware of whether there's, someone behind your back, you tune into certain ways of attending that are different frequencies in your brain, actually. And if you want to sit quietly and focus, that's yet another set. And then understanding like what your internal state is called interoception. We can learn to feel everything in our body. I'm sure like Elizabeth could tell us about that, because actors and actresses are experts at interoception, like getting into different bodily states. And so, it's a matter of like trying to learn different types of focus. A lot of people who are mindfulness experts and meditators, have techniques for doing this.
Wow.
I would say also in machine learning, we talk about generalization. So there's memorization, right? Where you just memorize everything you see. But in order to be really intelligent, you need to generalize to future situations. And so to some degree, I think of intuition as generalization from all of your experiences. And so like Andrea said, it's a form of, in some ways it can be viewed as a form of memory, but it's not a specific memory, but it's this integration of all of the memory you've had together.
Yeah.
And the realization of it. And so, you wouldn't have the intuition at all, right? If you hadn't had any experiences like it. So you haven't had exactly that experience, but you've had a whole bunch, in your brain, subconsciously even, is extracting all of those similarities and, giving you your intuition about what you should do.
Yeah. And some of our preferences are like intuitions too. So there's an area of the brain, the amygdala, that I mentioned earlier, that sometimes I call the like smart gut. It's like a fast learning system, and we're often not aware, but you can take many other brain structures offline and sort of still end up in a place that had a high amount of rewards if that structure is intact. So you can be guided particular places or into particular decisions without recognizing it. And some of that is because you're still making these predictions that Jenny was talking about based on past episodes, but it's sort of sub-threshold.
So is there an overlap between instinct and intuition then, or is it, or
high amount of rewards if that structure?
Sorry, Emily's on her way in. Sorry, we interrupted you.
Well, it just sound like in the description, and I'm probably just confusing it, that intuition is highly based off of prior experience, and is instinct something hardwired in like genetically from our predecessors?
Yeah, I mean, it's interesting there. I would say yes. I mean, in this same structure I was talking about, like you even have it evolutionarily conserved. Like you can take a laboratory rat, some rats, not all, and they'll have fear responses to fox odor because it's a predator, yet they've never been exposed to fox.
Yeah.
So that seems to be somewhere in the genetics of the rat.
Yeah.
You know, like that particular rat strain survived, you know, fox predation or something.
Yeah.
It's there. So you never know quite what it is.
Yeah. It's fascinating. Thank you for your question. Is that your name?
Tabaluga Dragon.
Oh.
That's just a nickname. That's just a nickname, not a real name. My real name is Sergi.
Sergi, thank you so much for your
Yes, thank
questions.
you.
And yeah, I saw your
Thank you
question pop up.
Thank you for answering so much. I really appreciate it.
Of
You
course.
me for a question.
Feel free to stick around. Emily, hello.
Hi, it's so good to see you.
Good to see you
Thank
too.
you already for answering my question about Lincoln.
Yeah, I just wanted to make sure, did that answer it about whether electricity would be able to kind of zap someone out of a memory loop?
Yes, it did.
Okay,
you.
fantastic. Okay, good. Did you have any other questions or?
I did. I was just wondering because in season 6, Fitz and Simmons, they go in a cerebral fusion machine where their brains are kind of joined, and then they experience a same sort of hallucination thingy. I'm just wondering if that is possible in real life to like connect the brains somehow. I'm not a scientist. I don't know the term.
Great question. Yeah. Would that be possible to connect two people's brains sort of outside their bodies?
So I think that's a super interesting question. And we've been doing some work trying to look at recording two brains at once, actually. Some very preliminary work. Other people do that work, but people will share, they'll kind of key on to each other's physiology. So one of the things we do is we have like heart rate, respiration rate. You know how you like go into a room and you can kind of pick up on someone's vibe? A lot of that is like how they're breathing and how their heart's beating. And some people key onto those things much more readily than others. And that can synchronize your systems to some extent. We don't know all the details yet, but it's a really cool thought. Like, you know how you have some friends where you feel like you just mind meld, like you can predict what they're thinking. So it's interesting. Or if you've played music and you get in the groove, you know, you're just right there with everyone. It feels very different. So, I mean, those are really interesting topics in brain science that many people are researching now, but we don't have like perfect answers yet.
Wow. Like the twin thing, you know, identical twins sometimes
Right.
kind of know, you know, think the same thing from 10 miles away or have a similar
Or like one of them falls and the other one's like, oh, my leg.
Yeah.
I don't know. Does that happen?
That's more metaphysical, but it's interesting regardless.
Yeah. Brilliant. We're right at 2:00. I mean, Sergi, you must be exhausted. I feel like, what is it now?
Get to
3
bed.
a.m.
No,
now?
it's perfectly fine. I'm incredibly happy to meet all of you. It's a huge honor, and honestly, I've been a fan of the show since almost the beginning. Honestly, from season 2, season 1 had a rough start, sure, but season 2 is just I got hooked. I became a huge fan. It's just you're incredible. Ian is incredible, and the whole team who worked on Agents of Shield is just fantastic. It's just top-notch storytelling and everything.
Thank you to the real life Fitzsimmons, Virginia and Andrea. I mean, it's just been just such a thrill to have you both on here. I'm in awe of both of you. I think it's so cool for me to have been part of a show that portrays science in a way that's exciting, because I think it is. And so I hope that today we've managed to inspire maybe some scientific journeys. I know both of you are very much
stimulated the audience.
Yeah. I know both of you are involved in education, obviously, in a big way, and are passionate about kind of bringing up a new generation of scientists and helping to inspire and maybe make science and as a more inclusive path for people. Are there any places that we can signpost people to that you would particularly like people to know about, or kind of programs that you maybe help facilitate? I didn't know if there was like websites.
Yeah, we're trying to start a global science of learning for education network to make education more rooted in the science of learning. And that's one place. It's kind of a, well, relatively new venture, and Virginia's part of that too. And then for people that are just interested in brain facts and stuff, the Dana Foundation has done a really nice job of that. So if you look up Dana Foundation, they always have these brain facts sheets that are super interesting. But you've probably done more for that than any of us, actually, because that was one thing that struck me. So I'll do 1 second of fanning here. And I watch very little TV in my life, but Agents of S.H.I.E.L.D. was one show that I watched with my family, and my son liked it particularly. And one of the things that I was so impressed with was like all the smart, cool women they portrayed. And so, you know, of course, Simmons was the science geek. So, and she was cool. So I think you probably inspired more careers than we have in that sense.
Oh my God.
So
well, I mean,
I think it's important for the media to do that.
Yeah.
I think everyone would agree. Women on Agents of S.H.I.E.L.D. are absolutely badass. They are like the best example, that they're like the prime example of how you do strong, independent women without bringing the men down. It's like, it's perfection. It's perfectly balanced. It's the way it should be, really.
I agree. Well, and we had a brilliant writer of this episode, Craig Titley, who I know that you know, Ginny, who deeply cares about the science and, you know, rooting it somewhat in facts. Yeah, we had a good team behind us, but thank you, Andrea. I think it's I'm happy. It always makes me happy that we kind of at least do science a solid by being, like, you know, loosely tied to the truth through a science fiction lens.
Well, half of science is imagination.
True.
Also, if you want a small local thing, we just started something called Pathways to AI. I put the link in our YouTube or in our Zoom chat.
Oh, great.
It's sort of starting out, but basically we're doing a variety of things. So far, what we've started is little videos that are still in process, but that are basically just little AI videos aimed at middle and high school students to just get them excited about AI. And AI related areas, AI being artificial intelligence.
Awesome. Oh my gosh. Okay. Thank you for a brilliant hour and a bit of just fascinating information. Thank you, Emily and Sergi, for your questions. I'm now going to invite the Zoom waiting room in. It gets chaotic and loud, and we'll just wait for a couple of minutes and then I'll end the Zoom. But yeah, thank you so much for being here. You guys are such an inspiration, and I just know that this is going to mean a lot to a lot of people who are thinking about science or interested in it, or just kind of, you know, we all have a brain, so we know we can all relate to the information that, that's being told, and there's lots of ways in here that you can unlock your potential, even if that's following your passions without necessarily knowing where it's going to lead, or just things like how your memory can be activated by smells and different senses, and yeah, just kind of investigating our own brains and how they work. I think it's just fascinating. So thank you again. God, I could just go on all day, but I'm going to invite the people to wave, and then we'll end it. But thank you so much.
Yeah.
Thank you.
Thank you.
Hi,
Bye.
Hi, Georgia.
Hi, guys.
Hey, Tessa.
Hi. guys.
Bye.
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 Hey,
Bye, everyone. Bye.
Bye, everyone.
oh my gosh.
Bye.
Kevin.
Bye.
Bye, Ward.
Hey, Nat, Jeff, Bernard. Hey, Coulson.
Bye.
Everybody.
Bye.
Bye.
Bye.